Good morning, guys. Since you are not going to be here for a couple of days, you're still quarantining, we're going to start chapter 10, which is a more descriptive chapter, then try to finish chapter 9 with its tests and calculations. So be sure you have your book available to look through the first section in chapter 10. The handout that you're going to be taking notes on will look like this. It's just a guided doodle notes to describe the kinetic theory of matter and solids, liquids, and gases that we have discussed just a little bit in the past. So, when you have your diagram in front of you, the title is in the top center, States of Matter and the Kinetic Molecular Theory. What that means is kinetic always means movement, which relates to how much energy something has. And the energy of particles in the three common states of matter is what this theory is actually about. So if you look to your left, the properties of gases reflecting the KMT or kinetic matter theory. Expansion of gases. Gases have no definite volume or shape. Gases can completely fill their containers. For fluidity, there are no attractive forces in gases. They move about freely. Gases as well as liquids are considered fluids. Density. Density, remember, write your little formula for density again that we covered at the beginning of the year. D equals M over V, which is density equals mass over volume. So the density of gases are about 1,000 that of a liquid. Compressibility. Gases are easily compressed, pushed into a smaller space. And of course, that increases the pressure. Add that little note because that's part of the gas laws that we'll cover later. Diffusion. There is a spontaneous mixture of gases which is caused by the random movement of molecules. You have to add that little phrase, random movement of molecules. And the example of that is when you spray perfume in one part of the room, within a few minutes, you smell it all over the room because the particles have bounced around and spread themselves out easily. Effusion is a little different than diffusion. Effusion or gas particles can pass through very tiny openings. Ideal gases versus real gases. Just like we were talking about a little bit in the last chapter, what you calculate is not always what you get. And so that's true of gases. So the theory applies to what we call ideal gases. Real gases deviate from the theory, especially under high pressure and low temperature. Okay, go up to the right-hand side of your diagram for the properties of liquids. For fluidity, liquids can flow and take the shape of their container. The density is hundreds of times denser than gases. Compressibility, liquids are only slightly compressible, forcing them into a smaller space. And sometimes that's simply because they have molecules of air mixed in. Diffusion, they can diffuse throughout any other liquid that it can dissolve in. So if you pour let's say sugar and water that's already been mixed into another liquid, it generally will disperse and diffuse. Surface tension is a force for liquids that pulls liquid particles together in order to decrease surface area. Surface tension is easily seen in water. It makes a perfect little round dot if it's on something that like waxed paper or something where it won't spread out. Capillary action is the attraction between the surface of a solid and the surface of a liquid. Capillary tubes are little tiny tubes in the lab, and if you put them, they're kind of like a straw. If you put them in liquid, the surface tension of the water will pull it into the glass tube, so that's capillary action. Now, water is considered a special liquid. We've talked about some of the special properties of water before, but they're just giving you the force that basically gives water all its special properties. The force of attraction is called hydrogen bonding. And remember, that's due to the fact that water is a polar molecule with charges. And we'll explore that more in the chapter. So the last of the common states of matter is in the middle of your chart there. Properties of solids, fluidity. Solids vibrate in place, they do not flow. Density. Solids are closely packed together, usually denser than either liquids or gases. They are not compressible. And then there's two basic kinds of solids: crystalline solids, which are structured in orderly repeating patterns called crystal lattice. And that can be a cube of metal, or it can be something like table salt, which you know are little tiny cubes, or it can even be a snowflake, because water molecules, when they freeze, have to go in a specific order or specific lattice. Amorphous solids are not arranged in any particular order, and it gives them their properties. And there are two good examples here. Anything made out of rubber is an amorphous solid, or glass itself. The way they solidify it, it does not have a crystalline structure. Now, the only other thing you need to do today, since this is a short class day, is I've given you a chart that looks like this. And the second page of it actually has two copies of what you need. So you just need to use either the top or the bottom. And this is a chart to reinforce the concepts we just talked about. So you cut apart the little half page on the second and paste them into the proper place in their diagrams on the first page. And we will check those tomorrow.